So welcome to Robotics 2. We are towards the end, going towards the end of the curriculum or the course. And we have only 3 chapters left from the entire textbook. And what we will do is we'll try to finish these chapters and then we will move on to the drone programming. So basically we will transition to quadcopter. And the way I'm going to teach quadcopter is I will give you the basic quadcopter equation, basic quadcopter dynamics. And then there are excellent MATLAB videos by Brian Douglas, where he discusses all the quadcopter fundamentals, the equations of motion, model-based control, which is called model-based design, and then finally programming the Parrot drone in that webinar series. So I would strongly encourage you to watch that, and it's actually very nicely done. So what we are going to do is this chapter is on path following. Next chapter is like path management. And then you have the last chapter, which is on the vision-based guidance. So the vision-based guidance, chapter 13, is exactly similar to the last chapter that we studied in robotics 1, which is on vision for the robotic systems. So what we are going to do is in today's class and in next class, I will try to finish chapter 10 and 11. And then chapter 12 talks about the A star, RRT, these types of algorithm. So I will give you an overview, but there is an excellent MATLAB series, like a cartoon series that kind of gives you the graphical way of how this whole thing works. So I would encourage you to watch that, and that would pretty much cover the material. And in the next three weeks, we will actually be focusing on the drones. So in the next couple of next week, I will talk about the quadcopters, quadcopter dynamics, and then we will look at programming the quadcopter. And my hope is that I would be able to I need to show you 2 or 3 demos in class, wherein actually how you can program the autopilot inside the MATLAB. That demo I would like to show you. And then if time permits, I will actually show you programming the quadcopter and doing a little bit path planning on the Mambu platform. So that way, that will give you some understanding of how you should proceed. But please understand, it's extremely important at this point that you start playing with the hardware. And again, as I said, if the drones are not working, if the drones fail, if your drone was working initially, I can guarantee you, other than prop, nothing is going to break. But if something happens, then I have few spare drones that we can swap. But just try to start playing with the hardware. Please do not wait till the last minute, because it may take longer time for some. It may take a very short period of time for some of you. So this is the control architecture that we have been looking at. So we looked at the unmanned aircraft. We looked at the state estimator, which is the Kalman filtering. And then we take this input from the state estimator, feed that to autopilot. The primary function of autopilot is stabilization. So for an example, even if you have an RC drone, whether it's a quadcopter or whether it's a fixed wing, the bare minimum autopilot is going to stabilize the drone. And then higher level autopilot, the bare minimum function of an autopilot is stabilization. And higher level function of an autopilot could be path planning or guidance or basically additional controls. So you have path following, and on top of it, you have a path manager, and on top of it, it sits path planner. And one thing I want to tell you that this, whatever we are going to talk in the path planning, the basic structure is similar, whether you are looking at the articulated robot arms or whether you are looking at the ground robots whether you are looking at the flying robots or whether you are looking at the underwater robots. So basic mathematical structure is the same. Now, one thing that we should keep in mind is robotics is on the borderline of applied math and engineering. So this is where some important concept in analytical geometry, topology meet actual applications. So basically, when we are going to look through the path planning, then we are going to look at the different algorithms. You will realize some of these algorithms have flavor of math. So you will see a lot of scary looking equations. But at the end of the day, what is important is how do we look at those equations and translate those equations into a working robot. And what I would do is, as I go through these slides, I will kind of explain you the math and I will try to give you some physical interpretation of what that equation means. Now, the simplest way for path following is something like this. I want to go from point A to point B. Now, UAV doesn't understand going from point A to point B. Robots on their own do not have the perception. What robots know is they can go from point A to point A1, which is very, very close to point A. So what that means is I need to find out a trace of points that would go from point A to point B. We did the exact same thing when we studied articulated robots. We generated a trajectory and the joint angles were manipulated so that the actual end effector went from start point to end point. Now, in the case of flying robot, the concept is slightly different. In the case of flying robot, what robot is trying to do is robot is trying to use seeking approach, which means robot is at point A. Now robots want to go to point A1. So for that time instance, the only objective that robot has is to go from point A to point A1. So this is something similar to the waypoint following. What that means is you have two waypoints. So you have start and you have end. And what's going to happen is, just like when you are trying to 3D print, you actually create some type of a mesh. You basically slice it. So in other words, I'm going to slice this path from S to E. I'm going to create a path. And then in this path, I'm going to generate these small points. And the objective of the autopilot is to control the roll, pitch, yaw, heading, airspeed, so that the robot goes from the previous waypoint to the next waypoint. Now, please understand, there is a subtle difference. What this is doing is following the path. It is not following the trajectory. What that means is I'm not specifying the amount of time the robots need to take to go from S to E. What I'm specifying is I want robot or the UAV to go from S to E, but I'm not specifying the amount of time that the robot needs to take. So basically, in the case of flying robots, what we do is we usually relax this trajectory following, which means we get rid of the time component. So time component is no longer present, and we only say that that robot needs to stay on that path. Now you can make this simple approach as complex as you want. So for an example, you can decide a trajectory that is a straight line path from S to E. You can decide the trajectory that has basically some type of obstacle avoidance. So basically you have a region, and then what you want to do is you want to avoid that particular obstacle. So you can make your algorithm very smart, but at the end of the day, the output of that algorithm must be these series of waypoints that you should be programming inside the autopilot so that the UAV can go from the previous waypoint to the next waypoint. And then this structure could be a rectangle, it could be a triangle, or what you can do is you can do a circle. And in today's lesson, we will talk about how do we construct these different profiles from very simple primitive shapes. So, but important part in the case of MAVs or UAVs is wind. So UAVs typically cannot fly at very high wind. There are some small UAVs that can fly when the winds are like 10 knots or 15 knots, which is 15 to 20 miles per hour of wind. But usually the UAVs are not designed to fly under high wind or high wind loading conditions. So you want to actually keep that in mind, because what's going to happen is because of the wind, the UAV path will be different. So you would have to continuously correct the UAV path so that it approaches the designed or the required path. Now, at the end of the day, there are different techniques and different algorithms. And as you go more and more into the studies and details, this path planning is an entire course or actually entire field in itself. And there are different techniques. Some of those are analytical, some of those are geometric, some of those are statistical. But what we are going to look at, we are going to look at a very simple technique, which is we are going to construct the path using a straight line segment and an arc. A straight line and arc. If you were to look at the MATLAB path builder function in the assignment that I asked you to use the MATLAB path designer function, it uses the exact same approach. It constructs the path using a straight line and a circle. So again, about 80% of the times you will be able to construct the path using a simple straight line segment and an arc segment. Another important thing is UAV, they have large turning radius. A UAV cannot turn in like half a meter or half a centimeter or maybe 10 millimeters. Typically, UAV turning radii are anywhere between 5 meters to 10 meters. So you can't have a UAV going straight and then turning. Sharp turns are not possible for UAV, especially for fixed wing. It's not possible. Quadcopters, you may be able to do it, but not for fixed wings. So you need to be comfortable, or you need to understand the limitations or the airframe limitations before you actually design the path. So what we are going to do is we are going to try to build the path from these path primitives. And there are other techniques where you can use higher order primitives, but those they actually come up when you actually try to make some complex topological path planning. So let's look at the description of the path. And again, some math will be discussed as we discuss the definition of path. But please understand, this mathematics is needed so that we can implement these mathematical equations into some engineering equations that can be programmed inside autopilot. So before I don't want you to be scared. You are going to see some math, some vector algebra. At the end of the day, all said and done, what's going to happen is you are going to have a PID loop. And that PID loop will take care of all the math that will be discussed in 4 or 5 slides. So don't let this math scare you, but I still want to discuss this math, because if some of you really want to get into the path planning, this is actually robotic path planning is a huge area of research. For example, driverless cars. How do you plan path for the driverless cars? How do you do obstacle avoidance? If you're a robot, you're programming the robot in the warehouse. I don't know if you go to Walmart or if you go to Fry's, you would see those cleaning robots. I don't know if you have seen. You have the robot that actually cleans. Or if you go to some restaurant, now they have robot servers. They call it Stella. So basically you have a robot, it has cameras, and that robot will actually bring the tray, the food outside. So there are some restaurants. Have you been to those restaurants? Yes, they have. One restaurant is Chennai Fusion Grill on Chandler Heights. No, sorry, on Chandler Boulevard. So they have that. The only problem with that robot is, if I don't know if you know, there is an Indian dish called dosa, which is like crepes. The issue with that is you have to eat it hot, otherwise it becomes soggy. So that Stella would bring any other dish except that crepe dish, because by the time that Stella robot brings the dish out, that crepe becomes cold and soggy. So I actually went there and I ordered something, and I saw that one dish was delivered, actually was served by Stella, and other dish was served by human server. So I was like, why that happened? And then he told me. So and then it has camera, it does not have LiDARs. But if you go to Amazon warehouses, where the warehouse robots are used for palleting and pallet moving, this path planning is used. So the concept that we are going to discuss here are very much relevant to different types of robots, even autonomous vehicles. So the objective is we are going to look at two primitive path definitions. One is a straight line path and one is an arc or a circle. So mathematically, if I want to define the path, what I want to define is I would like to define that with respect to two vectors. So I have a vector R and then I have a vector Q. So these two vectors are needed to mathematically define the path. So R vector is actually shows you where the path is beginning, and vector Q shows the direction cosine. It only shows in this direction my UAV needs to go. Now please understand, this is the desired. Okay, so this is the desired path, but actual path of the UAV may not be the desired path, and your UAV would be somewhere else. What that means is there is going to be some error, and this error is nothing but the vector difference between P and R. P and R stands for the current position of the UAV and the desired starting position of UAV. And at this point, I will develop this math, but I want you to understand, at the end of the day, I want to design a control algorithm so that this error P is minimized. So I'm going to design a control algorithm to minimize this error. Now, how do I minimize this error? To minimize this error, I need to control the heading, or if I need to control the course if there is some wind loading. So what I need to do is I need to control the course of the UAV or the yaw direction in which the UAV is going, and then somehow I need to minimize the projection of the error in the x direction, which is EPX, and the projection of error in y direction, which is EPY. So somehow what I want to do is I want to reduce or minimize this error. But this error, once again, is not a scalar quantity, which is not like theta desired minus theta actual. That is not the error we are looking at. This error has two components to it. This error has a horizontal component and this error has a vertical component. And we are assuming that the path and the UAV, there is no error in the altitude. Just you have the north and east. So you have X and you have Y error. So we want to minimize this error. Now, once again, we are looking at different coordinate systems. Remember, we have this inertial coordinate system. We have this body coordinate system. This is body coordinate system. And since now we are dealing with the path, we have this path coordinate system. So right now, please understand, there are multiple coordinate system. We cannot add dollars to pesos, dollars to dollars, pesos to pesos, which means at the end of the day, we have to decide on a single coordinate system and bring everything into that coordinate system. Why is this important? Because please try to understand, we have control over the heading of the UAV. If you have external wind, you have course. Heading means yaw without any external wind. Course means yaw added with the side slip because of the wind, and now you get the course. So that is something we have control over. But that control is in the body frame of the UAV. The vector R and vector P are defined with respect to the inertial coordinate frame. But at the end of the day, we want to travel on the path where path is defined by the vector R and the direction cosine Q. Everyone understood this? So this is where what we need to do is we need to use the mathematical tools to consolidate everything so that we can apply the controls in body coordinate system so that the UAV can follow the path in the path coordinate frame. Everyone understood this? So that is why the next few slides are gonna get into details of what exactly is this tracking problem. Tracking problem is actually, you have this UAV, you have this error, and now this error has two components, EPY and EPX. And what I want to do is, I want to define this coordinate transformation. I want to define this coordinate transformation because this is very important. P is defined in the inertial coordinate frame. R is defined in the inertial coordinate frame. But error is in path frame. So I have P that is defined in the inertial coordinate frame. This is with respect to inertial coordinate frame. R is in the inertial coordinate frame. So this error, what we are getting is an inertial coordinate frame. But what I want to do is I want to perform the projection of this error onto the path coordinate frame so that it's on this line. And how would I do that? Please understand, this transformation is achieved by using this chi q, which is the course angle with respect to the direction cosine q. So chi q is basically the course angle with respect to the direction cosine. So once I use, and believe it or not, this is the same rotation transformation that we have been using in robotics 1. This is the rotation about z. Can you see that? Cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, 1. This is the rotation about z axis. And once I use that transformation, all my errors get transformed in the error in the path px and py. Now, what I want to do is, if I want to look at the actual p and r, the error, that is nothing but the component of ground speed. Vg is nothing but the air speed, and so basically the ground speed is nothing but, if that aircraft would have been on the ground, not in the air, what would have been the speed of the aircraft? So what I have here is this guy, and I'm going to assume that EPZ is 0. So what I have is, I have this component of ground speed, and that relates to E dot Px and E dot Py. And now what's going to happen is, I'm going to use some type of a PID control. I'm going to use some type of a PID control to minimize that error. And that error, which is nothing but EPY, which is also called as the cross-track error. This error can be slaved to 0 or driven to 0 by adjusting or commanding the course angle. So basically, once this is the equation that you program inside the autopilot to minimize the error in E dot Py. What does that mean actually? Actually, it means very simple. You want to go in this direction, your UAV is going in this direction. What is the most logical thing to do is change the heading. And how far to change the heading? That depends upon the B chi dot and Bx, because you want to change the heading, but clearly there will be some oscillations. And then finally, what you want to do is you want to minimize that error so that the E dot Py approaches 0. What that means is chi minus chi q, they go to 0. And that chi minus chi q will go to 0 as long as this equation that you see has the poles on the left half plane. So basically, you choose the poles. In other words, you choose the Bx dot, a B chi dot, and Bx. Think about it like sort of the proportional and derivative gains, so that you actually minimize the error. Now, there is alternate way of visualizing this. This is just an alternate way of doing it. Yeah, that is exactly similar. So, but or you can say that you are using thrusters. If you are maneuvering a spacecraft, you can do the exact same thing. How you achieve it, what actuators you use, it's up to you. But mathematically, this is what we are doing. The other way to do this is basically, this is the concept of vector fields. And if you look at the concept of vector field, is basically, there is this concept of flow. Flow means in what direction the vector field is traveling. So in here, you can actually come up with the equation for the course using the concept of vector field. Now let me give you sort of the visualization. For example, you want to go this path and you have this UAV over here. Now, there are multiple ways to do the course correction. One crude way of doing the course correction, if your UAV is going in this direction, you basically turn this heading and start going in this direction. But please try to understand, as you cross this, you again change and then you go back. Cross this, go back. Cross this, go back, and kind of oscillate. That was the previous algorithm. Now here in the vector field, what's going to happen is, as you are approaching this desired path, you are making these incremental changes in the heading, just like what is shown in the vector field. So rather than going straight, correcting, going back, instead of doing like that, what you do is you are continuously doing the course correction so that the UAV gradually is correcting its course so that chi q and chi are equal to each other. Mathematically, that is the equation that is used. And what that means is, if you look at why this particular tan inverse function is used, because tan inverse function adds the required smoothing for the correction. So what you do is, instead of going back and forth and correcting, you add that course correction in a smooth fashion so that you are incrementally changing the value of chi. Now, some of you may ask me, mathematically, this is good. So what does it mean in terms of actually programming the autopilot? At the end of the day, what you are going to do is you are going to manipulate the heading loop in every iteration. So every iteration, you are going to change that heading loop. Again, the problem with this vector approach is, even though you may have your vector field turning, but the UAV has a finite turn radius and it needs finite time to make that turn. So that's why you have limitations on the large path and the small path that would actually achieve the type of transition that you need to make to change the path. Now, again, we talked about it, and I don't want to emphasize less on this, but Lyapunov's method can be used for a lot of applications. And the reason Lyapunov's method can be used is because energy principles are very fundamental to the functioning of the universe. For the simple example is conservation of energy. Energy can either be created, energy transforms into entropy. So all these energy principles that are valid all the way from the celestial bodies, all the way to the nuclear forces, and even quantum mechanics. So what you can do is, you can actually formulate the problem in terms of a Lyapunov function, which is an energy-like function, and you stipulate that energy function to be negative definite, which means the rate of change of energy is less negative, which means the energy drops down as the time goes on. And then you see the system is stable. So you can actually define, if you can find an energy function, and if that energy function derivative is going to 0, then you can say that consequently the error is going to 0, or the total energy is going to 0, and so on and so forth. So tracking problem can be defined in terms of a Lyapunov function. What that means is, you can define a Lyapunov function which is something like this. So y square, because the Lyapunov function needs to be positive definite. Whether EPY is positive or EPY is negative, your WEPY, the Lyapunov function, will always be positive. And what we are going to define is, we are going to define this course controller, and then we are going to find out the derivative of this Lyapunov function. And what I'm going to do is, I'm going to substitute the value of EPY, and I'm going to substitute the value of E dot PY, because please understand, since this is the function, the derivative is going to be EPY multiplied by EPY dot. So this is going to be the derivative of W dot. And if I can show if my W dot is going to be negative, then I can say for sure that my error EPY is going to go to 0. This technique only tells us this approach, like if the Lyapunov function is positive definite and the derivative is negative, then the system is stable. But it does not provide any sort of technique or standard approach to find what that Lyapunov function is. What that means is that gives only the sufficient conditions, but not necessary conditions, which means if you use a Lyapunov function and it doesn't work out, that does not mean the system is unstable. That means we may not have found the correct Lyapunov function. But if you find a Lyapunov function and that is negative definite, the derivative of it is negative definite, then you can say for sure the system is stable. So you can use the Lyapunov approach. So we talked about the lateral tracking and we looked at how do we minimize EPY. Now what I want to do is I want to look at the longitudinal tracking problem, and the purpose of longitudinal tracking problem is I want to minimize EPX. And the way we will do it is we have the UAV, and what I'm going to do is I'm going to look at the projection of this error into this plane, which is called as QKI plane. So when I look at the projection of the path onto the QKI plane, what happens is I get this error, which is nothing but the composition of HD and RD, and the total error is nothing but HD. Now, please understand, my UAV is somewhere over here. So, and I want it to go follow this particular path. So I need to relate two terms. I need to relate this term, which is over here, and I need to relate this term. So again, what I need to do is I have to use the similarity of triangles and then find out the geometric relationship between the terms QD and the terms HD. So as you can see from similarity of triangles, I get this equation. And then what I do is I actually implement this desired altitude, which is HD, which is function of R, P, and Q. R and P, they basically define the error, and Q actually gives me the direction cosine in the direction of path. And then what I'm going to do is I'm going to choose HC such that the error between the actual H and the desired HD, desired H, which is HD, is minimized. So what does that mean? Okay, so I just want to, so this slide and the next slide give you the geometric interpretation of path error. So geometrically, you have a component of error that is resolved onto the plane, which is Q and Ki. So second is actually quantifying the magnitudes that we want to control and the magnitudes that we actually know. So with that desired altitude equation is relating the quantities that are dependent on the current state of the UAV, and we are trying to calculate the desired state of the UAV. And at the end of the day, what we want to do is we want to come up with an algorithm so that the current state of the UAV approaches the desired state of the UAV. That's what all these two slides talk about in terms of vector notation. So what do they translate into? They translate into basically this simple equation. And at the end of the day, whether you like it or not, this is going to be a simple equation that involves some type of a PID control or the second order control. So as you can see here, and for this, what you do is you add some conditions, if else then type of conditions. And for that, you can either write if else type of conditions, or you can use state flow machines. So you use the state flow machine. And what you do is you have HS, HC. So this is the output. This is the input. And believe it or not, we derived this equation in chapter 6. And then what we do is we actually find out this error, HC minus H. And at the end, we come up with this error dynamics. And then what we do is we tune the gains so that this error equation basically is controlled. And you can use the final value theorem to actually find out the steady state values, and then you will get the steady state values of the error, something like this. Now, UAVs, you can't do a 0-degree turn, which means the aircraft cannot turn where it's actually flying. It needs to take a finite radius. So what we want to do is, you want to find out the smallest angle the aircraft can turn given its geometry. So there are different algorithms, and again, this is one algorithm, and wherein what you do is you define the path, parameters, you actually find out the chi-q, which is the desired course. Then actually you look at the error in the course. As long as this error is less than certain value, you can actually make the course correction. And as long if that error is greater than certain value, you actually turn in the other direction, and then basically repeat the loop till you have achieved the desired turn. Now, I don't know if you have any experience playing with Pickhawk or any flight controller. What they have is they have something called as the loiter mode, wherein you can program the UAV and the UAV can loiter in certain radius. So this orbit following algorithm is actually implemented in the loiter logic of the Pickhawk. So again, next few slides are going to give you the mathematics of the orbit following. But at the end of the day, the last slide, which will talk about the actual equations that need to be implemented in autopilot, are simple PID or transfer function models. So the idea is, again, this is the mathematical definition of orbit, because as soon as we try to define the orbit, understand orbit has three-dimensional representation. Orbit can have X, orbit can have Y, orbit can have Z. For example, orbit can be horizontal plane, orbit can be inclined, or orbit can be something like a closed loop, so topological loop. So that's why it is in R3, which is X, Y, and Z, three vector spaces. And I want you to understand that you will hear this term again and again, something called as the Hilbert space. So, okay, have you heard this term, Hilbert space? But if you are not, you will take robotics courses and you will notice that they will talk about this Hilbert space. What is Hilbert space? It is a space created by Hilbert. No, I'm just kidding. So please try to understand, if you want to define a vector in 2 dimension, if you want to define a vector in 2 dimension, what do you say? You say it has X and it has Y. So basically, to define a vector, you are gonna say X comma Y. So which means you are gonna need 2 values. So this is R square. If you want to define the plane or a vector in 3 dimensions, you are gonna need X, Y, and Z. So you are gonna need X, Y, and Z, which is R3. Now imagine in just your mind that you want to define a vector in 4 dimensions. If you want to define the vector in 5 dimensions, if for example you want to define a cotonian, cotonian cannot be defined in 3 because there are 4 components. Similarly, imagine if you want to define a vector which has 5, 6, 7, 8 terms. We may not be able to draw it, but in mathematical structure, that vector exists somewhere. Where does that exist? We know a 2-dimensional vector will exist in R2. 3-dimensional vector will exist in R3. 4-dimensional, 5-dimensional, 6-dimensional vectors will be defined in those 6, R6, R7, R8. Those vector spaces are Hilbert spaces. What it means is, as long as you go beyond V, R4, R5, R6, the spaces that we define are Hilbert spaces. And that is the loose definition, but to define it as a vector space, you need to meet certain mathematical definitions of vector spaces. And basically, you should be able to perform the matrix operation. Then you need to have the topological properties that all the vector spaces have. But in other words, Hilbert spaces give us a mathematical structure to define vectors in 4, 5, 6, 7, 8, 9 dimensions. Okay, that being said, so now P orbit has a vector space which is defined in 3 dimensions. And here, what we have is our orbit is defined by means of a scalar quantity and actually a vector quantity. And basically, you are defining a center. So you have this center at C. You have a scalar radius rho. And then what you have is you have direction, or also called as spin, defining clockwise rotation or counterclockwise rotation. And if you translate these definitions into the polar coordinates, this is what you get. And I'm sure most of you will recognize this as an equation of a circle. But this is not limited to the equation of circle, because in higher dimensions, you can have a sphere. You can have some circular structure in 4th dimension. You can have some circular structure in 5th dimension, 6th dimension, and so on and so forth. And what you have is, you have this angle or the spin angle, which is given as the tan value. Now, this is where the mathematics meets the engineering. So at the end of the day, what I want you to do, I want you to take this UAV and have it follow the circular path. So from engineering point of view, what I'm going to do, I'm going to make sure that my heading is continuously changed so that I go from the previous point on the perimeter of the circle to the next point of the perimeter of the circle, maintaining my heading, which is perpendicular to the normal. So what that means is, think about it like my UAV is sort of circling around the center. How would I achieve this mathematical equation in in something that I can code in terms of autopilot. So clearly, what I have is I have a Pn dot, which is the velocity in north direction. I have the Pe dot, which is the velocity in east direction. And I'm going to convert this into polar coordinates. And basically, I will have two quantities. And these two quantities are nothing but d dot and dphi dot. And basically, if you think about what this is telling, this is actually giving me the spiral, and what I'm going to control is I'm going to make sure that that spiral does not converge or diverge. It stays where it is. And the way I achieve that is implementing the control on d, p dot, and pi double dot. So once these controls, basically, if I control these, what that means is the path of the UAV will be a circular path. If it tries to go outside the circle, basically there will be correction in heading and correction in the spin, so that the UAV will come back to the circle where it's supposed to be. And that exactly is happening in orbit following. Now, some of me ask me, all this is good, but then what does that mean in terms of equation? So in equation, basically what we do is, when my actual radius is greater than the desired radius, what I do is I perform the course correction so that UAV comes back to where it's supposed to be. When my UAV is actually circling at the desired radius, I do not change the course. And then I have this equation that will be implemented in autopilot that will make sure that the UAV is following this orbit. Now, you can use again the same Lyapunov type of technique to see if the orbit that this UAV is making is stable or unstable. What that means is you program the UAV to follow this circular path, and all of a sudden you have the external wind. And because of that wind, the UAV kind of is deviated from the path. Now, the next question is whether the UAV will come back to its original path, or it will stay at the deviated path, or it will continue to deviate. So to track that, what you do is you actually use the Lyapunov function type of approach. And again, as you can see, you define this Lyapunov function and then find out the derivative of Lyapunov function and show that this derivative of Lyapunov function is less than 0, which means the controller that you have designed is stable. Now, believe it or not, Lyapunov technique can help you build very cool controllers very quickly. And I'm sure if you take courses in linear system theory, yeah.
Just Lyapunov is just telling us if the course is stable or not, right?
No, what is telling me is the control algorithm that I have used. If I use this control algorithm, whether the energy is becoming 0 as the time goes on. As the energy is becoming 0 as the time goes on, which means system is asymptotically stable. That all is this Lyapunov function telling.
Why is it important to check using this? I mean,
Okay. All right. So this will take a little bit more time, but I'll try to explain. So PID, or for that matter, the transfer function, or the state space, linear state space control techniques. All those control techniques are local control techniques. What does that mean? It means the domain of attraction or basically the domain of convergence for these control techniques is local. If you have a system, you cannot design a global controller unless you use some energy type of approach. If you look at the dynamics that we are looking at, the UAV dynamics, even for the path planning, is nonlinear system. For the nonlinear systems, the techniques like PID or linearization, feedback linearization, backstepping, and the plethora of nonlinear control techniques, almost all of these techniques are local in nature. What that means is as soon as the dynamics crosses that particular local region, that controller will not work. Lyapunov technique is the only technique that gives you the global control. It means right now I know for the fact that the control that I have designed or the control, basically the equation that I have come up with, that equation is valid everywhere that UAV is going to fly. What that means is this controller will control the system globally, not just locally. This is not a PID. This is the global control. PID is a local control. That's why the Lyapunov based techniques are actually important. So they give you the global control. They and they give you the global control because they are based on the fundamental physical laws like energy. If you take a course from electrical engineering in nonlinear controls or adaptive control, or even simple linear signal systems and signals and systems, they will discuss Lyapunov techniques in a lot more detail. But I can tell you, using Lyapunov techniques, you can design some very cool controllers very quickly. And the beauty of those controllers would be, at the end of the day, what is a controller? Controller is a mathematical equation. And what you do is your hardware will take that mathematical equation and then apply the actuator commands as per that algorithm so that the system is controlled. Once you design that equation, that logic, that algorithm using Lyapunov technique, then you know that that equation will work anywhere in the operating region of the dynamical system. That is the beauty of Lyapunov. The problem there is that control may not be the optimal one, which means, yeah. Go ahead.
Since Lyapunov.
Lyapunov?
Yeah. The ideas that we want to transfer a local control effectively can move it over to a global one, but then we still use a linear control method on top of it.
So typically Lyapunov techniques will give you a nonlinear control logic. It will not give you a linear control logic. The only time the Lyapunov techniques will give you a linear control logic if the system itself is linear. But most of the times the Lyapunov techniques will give you some equation that is nonlinear. Okay. All right. At the end of the day, all that mathematical jugglery led to this equation. And we used Lyapunov techniques to show that this mathematical equation will stabilize our UAV, which means if the UAV is following this orbit, if we use this control equation, if UAV goes out of orbit, but again, it will still come back to the original orbit. This is that equation is, yeah.
The A orbit, is it like also available in manual, depending on the size of the plane and stuff like that?
Yeah, so basically that depends upon the airframe size.
So we don't have to use the signal control method for tuning and stuff like that.
We are not looking at PID. So basically this Lyapunov technique is, PID is at the end of the day is a linear technique. Lyapunov technique is a nonlinear technique. PID gives you the local control. Lyapunov technique gives you the global control. Something to keep in mind. Okay, and again, the problem here is you can make this more complicated by adding some few more terms, and then you actually add the effect of something called as the roll feed forward. And what it means is basically you get some non-zero error, which is because of the effect, parasitic effects. And then what you do is you basically add the trimming condition, you add the turn condition, and basically at the end of the day, what you do is you basically add some type of a rolling condition. Now, I tell you what this equation actually logically. It is impossible for a plane to purely yaw because of roll and yaw coupling. The previous algorithm, we came up with this nice mathematical equation that told us to control the course. When I say control the course, what that means is control the yaw. When there is no wind, the course becomes yaw. Unfortunately, as we control yaw, because of the yaw to roll coupling, you are going to get some roll that may be undesired. So what that means is as you are tuning yaw, you will have to do the roll correction so that you have proper turning. So that's what all that means. And again, these equations again become super complicated because now what happens is if you add wind to it, then basically your heading becomes coarse. And then as you can see, our friend Kai comes in the picture, and then the equation for the feed forward of roll becomes more complicated because all these components of wind, Wn, We, Wn, We, all these terms that they propagate. But at the end of the day, what that means is if you want to achieve a controlled coordinated turn, then you need to control the yaw and you need to control the roll. So that is what it is. Now, the next part is this Dubin's airplane model. And again, this is actually the part of the next lesson, and I will talk about it in more detail. So Dubin's model is a mathematical technique wherein you are defining the path in terms of sequence of operations, not in terms of mathematical expressions that we talked about, but you are trying to find some sequence of operation. So basically, the typical sequence of operations are the straight line flight, left turn, and right turn, and then you actually use the Dubin's logic there are four patterns. You go through those patterns and come up with those different transition sequences. So, but Dubin's technique we will discuss in a lot more detail in the next chapter. And this 3D vector path planning, it's actually not part of the textbook, but this is actually given for reference from this textbook, from this paper. So again, I want to mention this because this is a very exciting field of research. Topological path planning, which means using the techniques in topology. Topology is how do you form knots? How many minimum knots you form? How can you convert a coffee cup into a donut? Converting, how do you change the shapes from one plane to other plane? So how do you look at the shapes? How do you stretch the shapes? How do you turn the shapes? How do you twist the shapes? The study of that is an entire branch of mathematics, which is called as the topology. Topological path planning is a very, very interesting and thriving field of research in robotics, wherein what they do is they take all these rich theories and techniques that are developed in mathematics and apply that for the path planning problem in robotics. And some of you may say, what the knot theory has to do with robotics. Here is a very simple problem. Imagine that you want your robot to follow a certain path, or you want your robot to perform certain maneuvers. What is the best way to perform that maneuver? And that mathematics is actually well defined in the theory of topology. So what you see, this 3D vector path following and topology and all that. Okay, some of you may not know this, but probably you have seen those school videos from Grass Flat, University of Pennsylvania, where you have those quadcopters flying together and then basically performing swarming and moving left, right, up, down, all that type of stuff. So the path planning for that is done using the classic topological methods. So yeah, actually Kaushik Bhattacharya did his PhD with Vijay Kumar on topological path planning. So again, then you do 3D vector path following. Again, this is part of the paper, not part of the textbook. And then what you do is you basically look at the manifold algebra. So basically you look at the manifolds, intersection of the manifolds, and the intersection of the manifolds gives you the path. So these are all rich mathematical tools and mathematical techniques. And all said and done, what happens is at the end of the day, no matter what these mathematical tools and stuff is done, at the end of the day, we get this equation and we program our autopilot with this equation. That is where engineering meets topology. After studying topology, after looking at the math, going through 10 or 15 pages of mathematical derivations, finally you come up with this equation, and that equation we program in Arduino. Everyone understood this?
All this calculation too much for a 32-bit processor.
The previous calculation is very complicated, but at the end of the day, final equation that we are going to get, usually it's very simple that can be implemented. If it is not possible on 32-bit ARM, then you use something like Linux embedded system like Parrot Mambo. Or if that is not the case, you use ultra high precision super high power sort of the edge computing type of technique. And so basically all that complicated math boils down to some equation, hopefully simple, that we program on microcontroller. And then based on my practical, so here is something very interesting. If you talk to field roboticists, which means who actually take these equations, program them on the robot and fly the robots, they will always say that these equations look good in theory, but in practice, you will have to tweak them a little bit or add some gains, tune the gains so that the actual field robots can work. But that is the fun between theory and practice. All right, I'm going to stop here. And if there are any questions, I would be happy to answer.